Hello and welcome to the logic of it all. In this video, we will talk about graph representation. So far, when we are talking about graphs, we mostly use the diagram of the graph as when vertices are some circles or some points on the plane, and then edges are lines or arcs that connecting some of those nodes. However, if you want to implement graphs and more importantly graph algorithms in a computer, we need to have a formal way of representing a graph. In this video, we will talk about two methods which are the main methods for representing graphs, namely using adjacency matrices and adjacency lists. Let's start with adjacency matrices. Let's assume that our graph has n vertices, which are labeled as v1, v2, up to vn. In that case, the adjacency matrix for that graph will be an n by n matrix, where each entry is either 0 or 1. And the value of the entry on the ith row and jth column depends on whether or not there is an edge from vi to vj. If there is, we put a 1 as that entry, and if there isn't, then that entry is 0. Now, to make this more clear, we have an example here where, as you can see, our graph has 5 vertices labeled as A, B, C, D, and E. And that means the adjacency matrix for this graph is going to be a 5 by 5 matrix that I'm going to draw down here. So 5 by 5 matrix. And we know that each entry is going to be either 0 or 1. And here's how we figure out which case that is for each entry. So let's say the first row is labeled with A, then B, C, D, and E. And similarly for columns A, B, C, D, and E. Now for the first entry down here, we ask the question, is there an edge from A to A? And we look at the graph and the answer is no, which means this entry is a 0. Then for down here, we ask the same question, whether there is an edge from A to B. And if you look at the graph, actually there is an edge going from A to B, which means that this entry is going to be a 1. Now for the next one, we ask the question whether there is an edge going from A to C. And if you look at the graph, there is no edge going from A to C, which means this entry will be 0. And for the next one, is there an edge from A to D? You see that there is an edge going from A to D, that's down here, and therefore this entry is 1. And finally, for the last entry on the first row, we ask the question, is there an edge going from A to E? And if you look at the graph, there isn't, which means that this entry is going to be 0. And then on the next row, we do the same thing for entries from for edges from B to A, B to B, B to C, and so on. And when we complete this graph, we are going to have an n by n graph of zeros and ones, which we call the adjacency matrix of the given graph. So, and here's the full matrix for you. So we don't always label the rows and columns, but obviously this is A, B, C, D, and E, and similarly for the columns A, B, C, D, and E. Now, one thing that we will see at the end of this video is we compare the performance of these two representations. And let me give you a quick example here. Let's say now you have the adjacency matrix. Your computer has this adjacency matrix, and you don't have really access to the graph, the diagram. Your computer doesn't. So all it knows about the graph is the information is in this matrix. Now, in an algorithm, let's say your algorithm wants to know whether there is an edge going from C to, say, D. Now, what it needs to do is it needs to go to the row representing C, which is the third row, and to the column representing D, which is the fourth column, sorry. So third row, fourth column, this is the entry. So it looks up that entry and it sees that it's a 1. So it realizes that there is an edge going from C to D. And if you implement this matrix, let's say as a two-dimensional array in a programming language, then we know that because of random access, this can be done in constant time, which means the time that it takes to find out whether there is an edge from a vertex to another, in this case from C to D, is independent of the size of the graph. It doesn't matter whether your graph has 10 vertices or 100 or 1,000. It takes the same amount of time to look up whether there is an edge from a given vertex to another. And that is the advantage of adjacency matrices. They're very quick if you want to check whether there is an edge between two given vertices. Now, the second method is called adjacency list. And in this case, basically, we create a list for each vertex. And in that list, we write down all the vertices that there is an edge from our vertex to those. Let me explain what I mean through this example. So we are going to have a list for A, another list for B. Probably I shouldn't write there. So let me write down over here. So we are going to have a list for A, another list for B, and then C, D, and E. So a list for each one of the vertices. And in the list for A, we write down the label for every vertex where there is an edge going from A to that vertex. So for example, we have an edge going from A to B. So in the list, we put B. And also there is an edge going from A to C. So in the list, from A to D. So I put D in the adjacency list for A as well. And that's the end of the list for A. Now for B, again, we need to look at the graph. We see that there is an edge going from B to C. So C will be in the adjacency list corresponding to B. And also there is an edge going from B to D. So D is in the list as well. And so on. And what we get at the end is a set of lists, one for each vertex. And this is called the adjacency list representation of the graph. And here's the complete list for you. Now, notice that for the last one, E, there is no edge going out from E. The out degree of E is 0. And that's why its corresponding list is empty, because you can't go from E to any other vertex. Now, as I said, at the end of this video, what we are going to do as the final step is compare the performance of these two representations. And based on that, we can decide, depending on the application and the situation, which one is appropriate for our application. So the first way that we are going to compare these two is through how much memory they use. Now, for an adjacency matrix, you need an n by n matrix. So for example, if your graph has 10 vertices, you are going to need a 10 by 10 matrix or a 10 by 10 two-dimensional array, for example. Now, that grows very quickly if the number of vertices goes up. So for example, if you have 100, then 100 by 100, that's 10,000. And then if you go to 1,000, then you need a 10,000 by 1,000 matrix. So you need 1 million entries and so on. And especially if your graph is what's technically called sparse, which means it doesn't have very many edges. Not a lot of the vertices are connected in the graph. So it's poorly connected, right? So for example, you have 1,000 vertices. So that means 1,000 by 1,000 entries in the graph. So 1 million entries. But most of them are zeros. So you're basically wasting that space. Let's say, you have only 1,000 edges. So out of 1 million, you have 1,000 ones, and then the rest of the matrix is 0. So a lot of memory or space is being wasted. But in adjacency list, we only write down in the list the adjacent vertices. So we don't have that problem with adjacency list. So that's in terms of the amount of memory that they use. In that case, adjacency list performs better, especially, as I said, if the graph is not heavily connected. Now, on the other hand, if you want to talk about how fast we can access to the information, how fast we can figure out whether there is an edge between two vertices, let's say V2 and V5, for example. In that case, as we saw before, we can do this in constant time. So it means that no matter how big the graph is, you can, in constant time, figure out whether there is an edge from one vertex to another. On the other hand, with adjacency lists, it may take a while to figure that out. So for example, let's say you have V3 here, and let's say your graph has 20 vertices. So in that case, when we want to know whether there is an edge from V3 to say V17, we need to look at the list. And it could be that in this list we have V2, V5, V7, V9, and so on. Now, in order to figure out whether there is an edge from V3 to V17, for example, we need to go through this list one by one and see whether V17 occurs anywhere in the list. And this list can be as long as, for example, if you have n vertices, it could be as long as n minus 1. It could be that all of them are here, or n minus 2 or n minus 3. And if n, the number of vertices, is very large, 1,000, 10,000, or something like that, then you see that figuring out whether there is an edge from V3 to another edge can take more than constant time. In other words, it depends on the size of the graph. So these are the the pros and cons of using adjacency list versus adjacency matrices. Adjacency lists use less memory, but adjacency matrices can perform faster. And this is something that you will see in computer science in many different scenarios, and basically it's called the time versus space trade-off.